We're going to look at using a Texas Instruments calculator to investigate the effect of the parameters in the logistic model that we discuss in the text. We will begin by setting up a graphs document, and instead of entering numerical versions of the logistic formula, I'm going to enter a parameter. The first parameter I'm going to use is going to be the limiting parameter in the numerator. So I will enter L, not 1. From here on it's going to look a bit like I've entered a 1, but I have not, and I will just enter the rest of it using 1 for the other two parameters, e to the negative x. And when I press enter, we will be asked if we wish to create a slider. And we're being asked if we want to create a slider for L. So I'm going to say OK for that. And what we have here in the bottom left is the slider. And I just want to look at what this does for you when you are investigating these graphs. I will just move this label out of the way. Notice it looks like the label has a 1 in it, but in fact that number at the top is not a number, it's a letter L. We have a value of L, which is 1, currently displayed on the graph. But what I can do now is, by moving this slider, I can actually change L. And I'm now on L equals, I think it's about 3. And can you see that we get a visual, now I'm at the top value, 5, and you can see that what we're doing by altering this parameter is we're altering the limit that the graph moves towards as x gets large. I'll now slide it to the left and we will go back down to lower and lower limits. But the interesting thing is you can actually take this into the negative, and you can see that this model now caters for situations in which populations or whatever it is we're modelling decline, and all the way through to -5. And you can play with this slider now and just get a real feel for the effect of the parameter L on the shape of the graph. We're now going to look at the effect of the parameter C on the shape of the logistic curve. I've entered a new function, and the only letter I've added is this parameter here, C. As before with entering L, I've generated a slider. And we can alter the value of C by sliding this slider. I don't think it's quite so obvious what's going on here, and in particular, if you slide the slider into the negative, you get a completely different shape of curve. So what I'm going to do is, rather than use this method, I will start a new document and I will put 3 versions of this graph on the same document to see if it makes the situation any clearer. Here we are with 3 versions of the logistic curve that differ only in the value of the parameter C. The blue graph has C equals 1, the red graph has C equals 2, and the black graph has C equals 3. As you can see, it looks a bit as if increasing the value of C is moving the graph to the right. But again, I don't think this is that obvious. So we will do a third investigation just to check whether our supposition that this is a horizontal shift is in fact correct. We're still trying to explain the effect of this parameter C on the shape of the logistic curve. What I've done here is I have removed the black curve and left only 2 values of C. The blue curve has C equals 1 and the red curve has C equals 2. What we're trying to establish is whether or not the red curve is merely the same shape as the blue curve but slid to the right. If it is, corresponding points should reflect the same difference between x coordinates. So what I've done is I have put in 2 horizontal lines. The black one is at f of x equals 0.4 and the purple one is f of x equals 0.6. I'm going to use the intersection capabilities of the calculator to work out the horizontal distance between this point of intersection and this point. We're interested in the x values, and I have done the purple one first, and we've got the results up on the screen. The difference between 1.099 and 0.455 is 0.6935. If our supposition that the red curve is the same shape as the blue curve, but just slid to the right, it has been slid to the right 0.6935. And what we ought to find when we do the intersection point that is here between the red curve and the black line at f of x equals 0.4, we ought to find that this horizontal distance is exactly the same, that is 0.6935. Now 0.6935 to the right of minus 0.4055 should be 0.288. So here we go. We will start and we will use Analyze Graph and go for intersection. On the Texas Instruments calculator, you have to select the graphs you are trying to intersect. We've got 4 on here, and the calculator needs to be told which graphs it's trying to intersect, so we will select the red one and the black one. And you get also this vertical bar here, which asks you to put a bracket around the intersection point you're actually interested in. We've already done this one, so all I'm left here is to do this one. And remember what we're hoping to find, that this distance is the same as this distance, and that this x-coordinate here should be 0.288. Well, here we are. That is what it is, and that confirms that changing the value of the parameter c in fact produces a horizontal translation of the logistics graph. Our final parameter to explain is the meaning of the parameter k. I've reset the whole thing and entered a new function in which we've set L to be 1 and the parameter C to be 1 as well. The result of putting a K here is that we generate a K slider. I've selected a window that I hope will show you what happens when I operate the slider, because by moving this slider what we can do is we can alter the value of K. As I hope you can see, choosing a large value of k means that the graph approaches its limiting value quite quickly. If we choose a smaller value of k, the limiting approach gets slower and slower. Going into the negative, this is a very slow approach, this one, by the way, so this is a very small positive value of k. If you slide k into the negative, you start getting decreasing values down to a limiting value. But again, this is useful. There are plenty of situations in which one might choose to use the logistics curve to see a decaying situation in which we're decaying to a limiting value as well. So here I think the slider method demonstrates the effect of altering k really quite neatly.